All right, good morning. Welcome to the session, Lessons about Accessing HDF Data in the Cloud. We have 5 speakers, so time is of essence. Just remember, if you want to ask a question, we have to use the mic, and then whoever is the speaker, they need to repeat your question, because people who are attending remotely are not going to hear, unless maybe, but let's assume they won't hear. So there are 5. The last one, that's me, it's under here, you see, so there are 5. And those who can, it's the wrong list. Whoever is entering your name from Noah, it's the wrong bullet list. I'm sorry. It's the one above, attendance and check-in. But no problem, we'll collect the data and resolve this issue later. Anyway, let's start. As I say, speakers have, let's say, 15 minutes max. I will be indicating somehow that it's close. So if you want some questions, obviously moderate your time. And so the first one will be Dana Robinson. He is the Director of Engineering and HDF Group, and he'll talk about state of HDF. Let me see, this is it. Yeah, there we go. You know how to use Windows, so you know how to go.
Yeah, is it being shared?
No. Well, the screen is shared, so I think it should be okay.
Can people see this?
Yes.
Okay.
So just go presentation.
I got a timer here. Started. Great. Okay. So let's see here. So let's see. This is F8. No. Let's see here. A slideshow. And beginning. All right. Are people seeing that? Okay. Great. Okay. So hi, I'm Dana Robinson. I'm the Director of Engineering. Oh, sorry. Sure. No worries.
Messed up. Let me just do this real quick. And then we should be good.
Okay, great. All right. Hi, I'm Dana Robinson. I'm the Director of Engineering at the HDF Group. And I'll just go over the state of HDF, including HDF5, HDF4, HDFU. So let's get started. Don't have a lot of time. So we'll go over the product status, what we've got going, what's been released. We'll talk a little bit about community engagement, and we'll talk a bit about our future plans for HDF. So product status. So this is the release schedule. This is on GitHub. You can see this. We have one of these for all of our products. Since the last time we were here, we've released HDF5 114.3 and 114.4. So with 114.4, we have float 16 support. We're trying to have more native support for machine learning types, including float 16 is the first one that we put in there, but we're looking also at like float 8, float 4, things like that, float 16. We've got some cloud optimized HDF5 tweaks in there. We've relaxed the page buffer checks to make it easier to work with cloud optimized HDF5. We've enabled allowing temporary security credentials. We fixed a bug with some chunk offsets. So if you're looking to just dive into the chunk offsets using the API, now we take the user block into account, which is a place where you can put some extra stuff at the beginning of the HDF5 file. We've improved data type conversion performance. And in this last release, we fixed, well, I didn't fix, somebody fixed and committed to us 35 CVE issues that are out there now. So you probably do want to update to 114.4. In the N-1 release in 114.3, we improved cross-compiling support. So if you've ever cross-compiled HDF5 before, you had to run H5 detect and do a bunch of things. We don't do that anymore. So now you should be able to directly cross-compile HDF5. And then we added some other cloud-optimized HDF5 tweaks. We've got like a 60 megabyte cache in the read-only S3 VFD that reduces the number of accesses that you have to make when you initially open a file. And then we also added support for Intel One API, AMD's AOCC, and NVIDIA's NVHPCC. You could build with it before that, but this now we've got official support for it, and we test with it. So the next releases that we have coming up, we have 114.5 will release in late September, probably the last release of 114, and that probably is not going to have any new major features in. I'll talk about that in a minute. And then the 114.6 release may not happen depending on what we're going to do with 116, which will be the next major release of HDF5. And on here, I have it indicated for next spring. I think it's going to happen earlier, probably in the late fall. And then we may not have 114.6. It may just be a bug fix release or something like that. So 116.0 will have complex number support. We have that ready now, but it requires bumping an internal version number, so we can't put that into a 114 release. We do want to change some of the library defaults to work better with things like cloud optimized HDF5 with modern storage systems. And then there's a few other minor API changes, like we're going from off-T, which is only 32 bits on Windows, to HDF-T, which is defined to 64 bits, things like that. Just a bunch of smaller things that should not significantly impact people who are trying to update. And we intend for this to be an easy migration from 114 without a lot of big changes that require people to modify their software heavily. And once 116 comes out, we won't be supporting 114 anymore. If you look back on this plot here, you see back in January of 2023, we're supporting 4 different versions of HDF5, and that was a lot of work. And so we don't ever want to go back to that. We just want to have one main release branch of HDF5 at any given time with just a little bit of overlap. So for HDF4, we still do maintain this. The last release was in February, and that was 4.3.0. In that one, we actually defined the public API. We used to just deploy all the header files, including the internal ones. We don't do that anymore. People may have noticed this if they ever included HDFI.h in their code, that now you can't do that anymore. We removed the XDR dependency, which is a problem for some people with building, and so that's gone. We've moved all of that internally and ripped out most of it. And it has a bunch of extra bug fixes in it. The next version of HDF4 is probably the last big change that I want to make to HDF4 to make it maintainable for the future. And that's to fix, there's some library naming inconsistency. So CMake and the auto tools build different names of libraries, and so we're going to unify that, and then Fortran will be in a separate library. So if you build things that are with HDF4 and you're going to be updating to 4.4, there will be some linkage names that you'll have to change and things like that. And this will make it, the purpose of this is to make this maintainable going into the future, right? We want to make sure that we can continue to build with new compilers and with new versions of CMake and things like that. We want to be able to just easily bring down things from HDF5 so that we can maintain this at low cost and NASA for the future. Then we have HDF View. What we've been doing for the past several years is really just making sure that HDF View works with the latest versions. And so the last version was 3.3.2 that was with HDF5 1.14.4 and HDF 4.3. The next version will come out, it'll be 3.3.3, possibly 3.4. That'll have HDF5 1.16 support and HDF 4.4 support in it. The one thing that I would like to fix in that is it doesn't really do paging. You have to load the whole file at one time. I'd like to fix at least that. But we don't really make a lot of changes to HDF View. That may change in the future though. And we don't maintain older versions of HDF View. We used to have HDF View versions that were based on 1.8 or 1.10, and we no longer maintain any of those. So for our release versions, HDF4 releases once a year, HDF5 releases twice a year, HDF View one time a year after the HDF4 release comes out, unless there's important patch releases and things like that. And we keep GitHub up to date in terms of the release schedule. So if you're ever wondering what's coming, we list the major features, we list the timelines so that everybody can see that. And we're working on automating as much of this as possible. If you look at our CI, we have extensive CI now. We test this with a wide variety of compilers. We try to make sure that it works in as many places as possible. And we also have links to the public C- on there, which points to even more things that we test internally. It's sanitizers and things like that. And we also, as far as the CVE issues go, we have a repository where we keep the files that expose those CVE issues, and we run that on every check-in, so we don't regress on CVE issues. So we're trying to be better about security, as I'm sure anybody who was affected by CloudStrike can attest. That's important. As far as community engagement goes, we have a working group meeting that's once a week on Thursday. It doesn't always happen. It's usually just when there's an agenda. You can edit the wiki or email me and we can add things to the agenda. It's to go over RFC, requests for comments. It's to go over important recent PRs. If people have technical questions, if they're developing a feature, like that's the forum for that. It's really for developers. It's not for technical support. Everybody's welcome to it. There's a Zoom link on here. We're working on getting a calendar invite set up that people can have. And there's we post on the forum the agenda and when it's going to happen, and we also have the wiki off of the HDF group wiki. We also have started working on a plugin working group meeting. We took one of these meetings and we started this summer, and the idea is that we're going to work on making a subset of the existing filter plugins first-class citizens that are built with the library, that are developed kind of at the same level that we developed the library and HDF4 and all these other things. That's the second Thursday of the month. If you're interested in that, if you want to have input into it, if you're curious what's going on, it's open to anyone. People can show up. We're always interested to hear how people are using filters and what sorts of things they care about, if there's new filters that they want to see. And this will be, the idea is for this to be a place where we test and build and deploy these kind of canonical filter plugins, but also for anything that we can find so that there's more provenance. Even if it's something that we're not specifically going to support, if we can find the code for it, if we can find more information, more documentation about who these things are for, we want to find as much out in the wild as possible and get it into this repository so that there's a record of where this stuff is, so that if somebody encounters these in the wild, you have some hope of trying to build the filter, find the library that was used for, and things like that. So another thing that we've started to work on is we've been over the years moving more from a more cathedral type of open source governance to a more bizarre form of open source governance. And one of the things we wanted— Bizarre, yeah, not bizarre. Sometimes bizarre. But one of the things that we're doing is we're taking Python's PEP infrastructure and modifying it to be useful for us. It's all open source, and so we can just clone it over. And so right now, if you look at this repo, there's nothing there. It's not open yet. It just exists on my laptop. But HEP1 will come out sometime in the next month or so, and that will, like PEP1, it will have the governance of how we're going to do this. And so if people want to change the library, if they want to talk about how the process for doing certain things in terms of deployments, in terms of like how we're just going to govern it, that will all be in here, just how it is in the PEPs. So look for this probably in September or so. It'll take us a little while to get this going. So for future plans, we're going to continue to work on cloud optimized HDF5 is really critical. People are putting a lot of data in the cloud, and we want to make sure that as much as possible, everything works well there. Machine learning optimized HDF5, better governance, and working towards HDF5 2.0. So for cloud optimized HDF5, again, I want to make the read-only S3 VFD a first-class citizen. Currently, it's something that's extra, and it doesn't have a whole lot of testing, and we want to have more robust testing and work more on performance of that. There's a feature in the library called selection.io that may be useful for the read-only S3 VFD, where we can take a lot of I/O and farm it out into a thread pool that then goes and gets it in parallel and pulls it back together. So we'll look at that. I would like to expand it to other cloud object stores. Right now, it's really geared around Amazon S3, and so I'd like to be able to support Azure and Google Cloud Storage. And then continue tweaks and enhancements. As Alexander's been working on stuff, he identifies things that we can do to make it work better, and we try to get those into the next major release of the next release of the library. And better documentation. Right now, there's videos out there, but we really need to update the user guide to include better documentation on how to use cloud optimized HDF5. And we want to take the same process that we've been doing for cloud optimized HDF5 and also do the same thing for machine learning. That has very different access patterns, and we want to spend some time over the next couple of months to try to understand better what we can do inside the HDF5 library to make HDF5 work better for machine learning training, for storing models, for things like that. To document things, have some examples, have some best practices. And as far as the governance, expand on the HEPs. We have our meetings, we may expand those. And then another thing that we have is, a long time ago, we had the technical advisory board, which is people who help steer HDF5 kind of in a bigger, more strategic way into the future. And so that's one of the things that I would like to restart in the fall, is the technical advisory board. And then HDF5 2.0. So the next major release of the library will be HDF5 2.0. This is a tentative feature release. This is on the website. We don't have any release date yet. But the most important thing, I think, is going to be multi-threaded HDF5, which is where you can have multiple threads inside the library at the same time. Or the work is largely being done with Lifeboat LLC. You'll hear about that today from Elena. Also with contributions from NVIDIA. There's sparse data storage, improved variable length data storage, also Lifeboat LLC. Crash proofing. So we want to make sure that we have ways, if your writer crashes, you don't ruin the whole file with that we can recover from it. We also have encryption and digital signatures. We got funding from that from the NSF this year. And then full swimmer, it's a feature. So we have the single writer, multiple reader pattern, where you can have one writer that writes out to a file and then multiple readers read it, but it's only usable in certain contexts, like if you're just extending a data set. There's a feature that was not fully finished and was not fully integrated into the library called VFD Swimmer, which is really full swimmer. It allows the single writer, multiple reader pattern to extend to all API calls and all sorts of things that you can do with the library. So there's a full list on GitHub, and we keep that updated. So, and then finally, I have a plug. We have the HDF user group meeting that's coming up August 5th to 7th in Chicago, Illinois. Might be a little late for people to plan a trip to Chicago at this time, but there is a remote option. It's only $50. Just covers our cost for hosting it. So if you're interested, you can go to the website on there. And that's what I have. 14 minutes, all right. Questions? Or do we want to go on to the next one and do questions at the end? How do you want to do it? Okay.
Nope.
All right. If you have anything you want to ask about HDF5, release schedules, how it's used, anything, just please talk to us. Thanks a lot.
All right, thanks, Dina. Let's see how we bring this. So now I think I open your. Oopsie. Wrong one. Close. Sorry to, I'm not a Windows user, as you can imagine, so it's a little. I remember, I'm going to EC meetings that long that I remember when these computers were all Macs. So the Windows users had problems.
You're too old now.
Yeah. All right, so the next speaker is Elena Purmal. She's the former director of software engineering in HDF Group and now successful small business entrepreneur.
Well, we'll see how successful.
Well, okay, small business, I always have to, so, but anyway, the host asked you to start video, okay. All right, I'm starting. So, Elena, you can speak.
But we can have to make it.
Oh, yeah, let me see. I think this is this how, yes, I think that's the one. Oh, it's a speaker now. How is this now possible?
Oh, this is
Oh,
fine.
oh, good. All right, okay,
This
good.
is fine. And
Okay,
how do I move slides with
I
these
think
errors?
with this one.
Okay, okay. Alexander, thank you for introduction and thank you very much for giving me this opportunity to talk about new developments in HDF5. So I will be talking about what we are doing enabling multi-threaded access to HDF5 data, adding new storage types that will allow us to store sparse data more efficiently and variable length data more efficiently in HDF5, and we're also introducing encryption in HDF5. So since we're not HDF5, we're not making HDF5, we really we're trying to make HDF5 just better. And we're a real company, we have website, I can answer info email, and we will like it because it's very competitive program to get 3 grants from Department of Energy, Small Business Innovative Research Program to introduce multi-threaded concurrency in HDF5. We are we're second year in the project, making good progress. It's very challenging to introduce multi-threading in legacy software, as was reminded us several times yesterday, and 2 more projects that are listed here. So as small business, we have to make a product. So our vision is right now to create set of plugins that will enhance behavior and performance of HDF5, such as subscription, multi-threaded access. But in long term, we really want to make HDF5 library multi-threaded with all features. We'll see how it will work. It is a challenge, but it's fun. So some terminology for my talk, I will be mentioning virtual file drivers. A virtual file driver is really I/O driver that maps users' data to storage according to HDF5 file format specification. So whatever storage you use as 3 object store, when you use virtual file drivers, you will at the end get logical HDF5 file mapped to the storage. Several years ago, there was another way of putting data into storage introduced into HDF5. It was virtual object layer, so-called Vol connector. And wall connectors can map HDF5 user data that's coming from HDF5 application to actually any type of storage and any format. So for example, we can read, if we create wall connector to ZAR, we can read ZAR files and write ZAR files through HDF5 interface using, say, for example, H5Py. And this was the path that allowed us to improve HDF5 library in many ways, because especially in HPC areas, there were several wall connectors introduced. And what essentially that architecture helped us to do, there is a layer that captures the calls and it can redirect through the original HDF5 library or through the wall connectors that users can create, or we have several HDF group created already to put, for example, data into Deos object store. There is a RESTful that HDF group supports that uses HDS server to put data in cloud. But if you go through the library, there are many drivers here. And you can put, for example, mentioned several times, there is a read driver that can read data, HDF5 file from the cloud. Those plugins are, those drivers and connectors can be written as plugins, so they are loaded at runtime, and it's very convenient. So how we approach to multi-threaded access? I will just, as you know, there are two types of programming. Essentially, if you want to improve your performance, you really have to look into parallelization of your code. And there are two known ways of parallelizing the code. It is for shared memory systems using message passing, and this is what was created in HDF5 from the very beginning. And there is another way that was introduced when first craze were appeared, that's shared memory systems, and they use threading. And there are special programming paradigms like with using OpenMP directives, P threads, window threads, and so on. And applications, of course, sophisticated applications, they, on current HPC systems, they use hybrid approach, getting really good performance. So, currently in HDF5, there is no multi-threaded support, meaning it is thread safe, allowing only one thread to come to the library. Because if you allow two threads more come to the library, they will corrupt memory data structures and corrupt data in the file. So we want to enabling concurrent access to HDF5 data, allowing multiple threads entering into the library without corrupting data. And why? First of all, it is much easier to implement using, for example, OpenMP. And current compilers from almost every vendor support C, C++, and Fortran with OpenMP directives, and the NumPy Python packages supported now. I/O is tricky, and I will not go into this. It's probably the talk for next year. So what is our approach? And you probably heard about this already yesterday several times. The idea is the same. When we need to get, if we make several packages that wall connectors use multi-threaded, we can allow threads come to the library, go through a virtual object layer, and then we have bypass wall connector that does known things for you. It gets through the library information about metadata, where to find raw data, and we will be hitting global logs. But after we get it, we can use multi-threading to go to storage. And why this work? Why? Because we did some experiments and it does work. It really speeds up your performance. We work with Blue Brain project, and they are simulating activity of a mice brain. And the file is very simple. It has like million of two types of data sets, and they are described here. So I experimented with they came to me and asked, listen, we cannot read the file we created, and we look into it, and of course they couldn't read, so we had to use HDF5, and we were using version 1.10. And what application was doing, it was just reading those data sets into memory for their modeling application. So we had to use page delocation, we had to use page buffer feature, which user may not know about. That's why we need to set defaults and enable some things by default. And finally, we could make HDF5 to work. So we were able to read this half terabyte data set in some reasonable amount of time. But what we also did, we used threads in application, and we used threads to read metadata from the file. And when thread was finding the data, it was going in outside the library and reading the data. And those 3 experiments, this is the time takes to read metadata and then to read data total. And the right column, 3 columns, it's the same experiments, but metadata was read from precompiled JSON file, pre-calculated JSON file. And you see we were able to achieve 5 times speed up, which was incredible because they really now could run the application. So this approach, believe me, works. Can you use the bypass wall connector that we already implemented? We just need to clean it up, but if you are interested, we can use it with single-threaded applications. And this is results for benchmark that is kind of trivial. We read contiguous or chunk data set by just HDF5 library or HDF5 library with wall connector and internal thread pool, and I don't know why I put thread twice, it's just a typo, and ran on Linux and Cray system, and we achieved 1.6 to 3 times scaling of this. So this is the blue column is HDF5 speed on Linux box, and red is the same program with the wall connector that spawns threads, and you see how performance scaling up to 8 threads or 5 threads in this case. It's really nice scaling, getting almost 3 times performance improvement. Does it work always? This is on Perlmutter, this is Cray, really nice scaling, but data set was too small and it was on that compute node, it was all in memory. That's why you see incredible speeds like 30 gigabytes per second speed. But if your application works with such files, once again, you gain the speed. With a bigger data set, we need to look and maybe tune a little bit, but we're still getting improvement when we're using threads pool to read data from the file. So sparse data storage. As you know, in HDF5, there is chunk storage mechanism. And for example, if your data is sparse, like presented in this matrix, when you store the chunk, of course you can compress and all those zeros disappear, but you will not know locations of those defined elements unless you read the data back and start searching where is your data located. So idea is to use different storage paradigms, which is called structured chunk, that can store not only your raw data, but also some metadata about your raw data. And in case of sparse storage, it will be locations of the data that will be stored within the chunk with raw data. This approach allows us to store not only sparse data, but also variable length data, because we can have, for example, 3 sections in the chunk and store locations of the elements, then store, in some sections, store the elements themselves, and in another section, store pointers to that third section that can find variable length data. It allows us to compress. We now have APIs to compress each section, and you can specify your pipeline. And I have a white paper listed here on the slides you can find that shows it really gives you advantage of saving storage and having information transparently where elements are located. And my last slide is about introducing encryption into HDF5. So why encryption? We're talking here about open source, open data, and so on. This is not about hiding your data. It's really about integrity of data that is not currently guaranteed by HDF5 library. HDF5 format is open, and really you can easily modify, say, attributes or data. You know where checksum is stored. You can modify checksum and compute. So if you want, you can compromise data very easily. At least encryption protects data from being stolen, changed, or once again, being compromised. And that just adds extra level of security for sensitive data, because HDF5 is used by industry and so on. We have phase 1. It will be available pretty soon if you're interested. By finishing, there will be 2 algorithms, and idea is that encryption comes as a pluggable VFD, and any encryption method can be used like we have with the compressions. So thank you, DOE, for supporting this work, and we have probably have time for some questions. Thank you.
Any questions?
Yes.
I have a question. What do you think is limiting your scaling when you're got your graphs for your plots for how your threads are?
Looks like we're saturating the network connection with the request. Once again, to be studied more, and this is a tricky problem on any system. We didn't get any scaling on Mac OS. And this looks like that on Mac, on some versions of the Mac, file system has global log, so it serializes, but it's much faster than even on supercomputer. That's why doing your work on Mac is really good. You get much faster results. You're not getting scaling. But multi-threading is not only about I/O, it's really improving your application because you can do more tasks, especially for visualization. Now, when HDF5 library is multi-threaded, it will be much easier.
Any more questions? No, keep it just there.
Okay, thank you.
So I have 2 questions because this is easy. So can you clarify of all these improvements that your company is working on, are they going to be eventually in HDF5 library in open source licenses like everything else?
The source will be open source that we're working. It may come with some license, and most of the source that we're developing for multi-threading will go into HDF5 because we are enabling multi-threaded wall connectors. It's not only our wall connector. There are already some wall connectors that are multi-threaded, but they cannot take advantage of multi-threading because HDF5 library has this global log. We have to investigate licenses, and I'm sure the license will be for those plugins, no cost or free, almost no cost for academic and agencies that support it, and we'll try to target applications that need those features. For example, MATLAB. Can they be with us and charge if they want to include this feature? For example, they have problem with testing because they use multi-threading testing environment, and HDF5 simply doesn't work on it. So we'll see.
So another question, sorry. The sparse data and the variable length data. Since also in DCIP there's a lot of people who are developing software that sort of accesses data in HDF5 files, not using the library. Will this storage that they're going to be proposed, is that going to be, shall we say, friendly to alternative methods for access, which depend on the contiguous blocks of bytes having the known meaning?
Right, yes. First of all, programming data model will not change. We're very careful about APIs. APIs will be extended. For example, we're extending H5P set filter function to eliminate this limit on data that you can pass to the filter. And the file format is open, it's described, and by the way, it's available for review, and there will be known ways of deciphering the chunk and APIs that will give you that data and say addresses of where you can find data in the chunk. So it will be the same user accessible, not maybe too much user friendly because it's really low level. You have to go use APIs to get this data.
Yeah, that API, that's what.
But they will be, yes, absolutely. All data will be, data from all sections will be available through APIs.
All right, thank you, Elena. No more questions.
Any more questions? Thank you.
All right, the next one is, let me remember, Kent Yang from HDF Group. Long-time supporter and working on Hyrex, connecting Hyrex and HDF5 library and everything in between. So I will, yes. Kent, can you share the screen, please? There you go.
Did you see my screen?
Yes, just go into the presentation mode.
Okay.
Or you go, Kent.
Okay. Yeah, I'm from HDF Group. I'm Ken Yang, and I'll switch to a different area application. How we can access HDF data in the cloud through OpenDAP web service. The HDF data I'm going to talk is not only HDF5 data, but also HDF4 data. They're all NASA HDF data. That's how we got supported and then we focus on. An OpenDAP service, OpenDAP hierarchy service. So how we can access HDF data in the cloud is through a hierarchy DMRPP module. DMRPP module is using XML file called DMRPP file to access HDF data without using HDF libraries. But to generate a DMRPP file, one need to use HDF libraries to obtain the user-defined attributes and also the key information to access data in the cloud. Of course, using DMRPs, the reason is to, can get better performance in the cloud to access data. Today, I'm going to mainly talk about the direct IO performance improvement. I'm using a report style. I'm not going to talk technical details a lot. Any questions about technical details, we can talk offline and Q&A. But basically, the purpose, DMPP already improved the performance to access data in the cloud. Can we further improve performance? That's basically the data IO stuff. And also, I briefly mentioned about NASA HDF4 and HDF US2 support through hierarchies through DMRPP. So that's my talk. And these slides, you see two charts. Basically, they are identicals. Let's focus on the upper part, the general approach. This is a pipeline of a popular hierarchy service, at least for NASA data, to handle NASA data, called File HDF service. On the left, you have HDF file, and it can either in the local disk or in the cloud. Doesn't matter. And DMRPP module will read the data into the memory, and then the hierarchy core will do some data manipulation, and then pass the data to the File HDF module. The File HDF module will write the data into an HDF4 file. This is this pipeline. And how we can improve performance on this service, because there is something special about this service and also NASA HDF products. Most NASA HDF products using in-memory compression to compress data, as you already know more about this. And one DMRPP module read the data into the memory. It has to decompress the data and then pass to the hierarchy core. For the other data service, the data value is already resumed, and then the hierarchy service will pass to the end user because they just want to obtain the data. But for this service, the end result is a HDF4 file. So for the same reason, to use compression to reduce the file size, so the File HDF module will compress data again, and before it pass to the generate an HDF4 file and pass to the user, just to reduce the download time. So this is how we can optimize with a simple approach. That's in the lower part of this chart, called approach with direct IO. So how about just pass through the data without doing any compression? So you can save you a lot of CPU time and memory, and then hopefully the performance will get improved. So I'm going to show you the next two slides So some performance comparison results to just by using direct IO and also without using direct IO, how it become, performance improved. So I'm using a Hyrax group, a Hyrax testing, real testing server hosted by OpenDAP group, I should say. And the service is like we want to check to obtain just one HDF5 file through Hyrax, through DMRPP, and then the output is a HDF4 file through this real Hyrax testing server. And I'm measuring the server response time. And the files I choose are all NASA HDF5 files currently served in the cloud. And they are using Hyrax to serve these products in the cloud. And I just show a few, but I test many of them. And like this global high resolution sea surface temperature, TRAPOMI, SSMI. One thing you want to see their file size, they are range from maybe about 1 megabyte to about 300 megabyte. But the thing, you see this chart, you see the speed up in response time by using direct IO just stand out. It can be more than 10 times faster to obtain the whole file for the if we measure the response time. Even for smaller file size, the speed up is about almost 70%. So we found that to handle the bigger size file, the benefit is even greater with direct IO. So I have this DayMap product is about maybe more than 3.5 gigabyte. And this Modis derived product is 4 gigabyte. Using direct IO, we can serve the data. It takes a little bit longer time, but it's big file, and but we can serve the data. But without using direct IO, Hyrax cannot really deliver this service because of the time limitation and the insufficient memory. And we found that really a big file, this CH4 level 4 file, which is 11 gigabyte. And then we think direct IO might help us. But this one, direct IO feature cannot be used because this file, they don't contain any compressed variables. It's really rare, but we do find one. So that comes to my next slides about the facts for the direct IO feature. First, Hyrax will use direct IO automatically. It's transparent and highly transparent to the end users. If you have this Hyrax that support direct IO, basically direct IO will be used to when it finds that it can be used. And it's variable based, it's not file based. So if I have a couple of variables in a file that we can use direct IO, Hyrax will do that. And the other variables will still use general approach. But these variables must be fulfill there are some restrictions. The array must be selected. The whole array must be selected. You cannot use direct IO for subset of variable, and also this variable must be compressed. There are some other case restriction I just ignore here or with me offline. But one thing I want to point out, direct IO doesn't work for some old NASA DMRPP files because those files were generated years ago. They don't contain the key information that needed for using this feature. So this DMRPP file need to be regenerated. I personally see there's many those kind of files in NASA distributed by NASA data centers. So if you really want to use direct IO, you think this service is useful for your end user, unfortunately, the DMRPP file need to be regenerated. And here, just brief summary, direct IO can help you, improve your performance a lot. But I want to point out, HDF5 direct chunk IO API used. So this is give credit to HDF group for this, not just, without using HDF library, but the whole process, we need to use HDF5 direct chunk IO API when, generating an HDF4 file. And also this feature is in the current Hyrax release. So people can use that either for cloud or maybe for your other service. So I'm going to talk briefly about the HDF4 work and US2 work through the MRPP. We received this task this year. Basically, NASA still have some HDF US2 products they want to serve in the cloud. Probably they're already in the cloud, and they want Hyrax to use the MRPP to obtain those files and serve to users. So first thing we do this, we have to map HDF4 to DMR, which is required to generate the MRPP file. And then we also make sure the MRPP file, there has to be, this basically necessary correct information in the DMRPP file so that the HDF4 file can be read through the MRPP module rather than through HDF4 library to access the data. So we encounter that HDF4 is totally different than HDF5. People should know this fact. It's not only use chunking and contiguous layout, they also use something called linked blocks. So we need to really write a whole chunk of another set of code to handle this. And we also need to handle the EOS2 and HDF4 geolocation data in a special way. To serve the user. So I'm just ignore the details. I'm going to the next slides. Basically, current status, we can successfully map and access the sample NASA HDF4 and HDF EOS2 products received from data centers. These products, they say, okay, we are interested in serving this in the cloud. So we receive from data centers, we implement that, we test that, they all can successfully be accessed through the MRPP module. We are still working on a better way to store HDF US2 and HDF4 geolocation data. I'll ignore details. But one thing I want to point out for this work, I benefit a lot for old HDF4 project called H4 Mapper project. That was back in year 2006 or 2007. NASA, Chris Linux and Ruth Thur from SIDC. Chris Linux at that time was GS Disk, and also worked with HDF group and supported by NASA to generate HDF4 mapper file. The purpose is to use that mapper file to access HDF4 data without using HDF4 library. So HDF4 mapper file is equivalent to DMRPP file. So I can go back and check the documentation, very good documentation, and also examples. I can quickly get this implemented. So I want to really thank NASA for supporting us in the old project, pay back for this work. So this my last slides just to show you that yes, we can successfully access HDF4 file through OpenDep's Hyrax the MRPP module. So on the left side is they are both panoply screenshots. On the left side is local HDF4 errors data, and the variable is topography, and then you can see this variable plotted, and then on the right is basically an HDF4 file I generated through Hyrax through the MRPP, and then we can see the result are the same. But this is just show you. You can see, clearly, but we also check in other ways to make sure that all the data are mapped correctly. So that's the end of my talk. I'm not sure about my timing. Hello? I cannot hear anything.
Yes, I have a question for you, Ken. So this NetCDF4 via DMRPP output that you showed in Panoply, is that basically Hyrax server on the fly accessing the HDF4 file and then generating a NetCDF4 representation that Panoply was understanding? Am I correct?
it's an HDF4 file. It's generated an HDF4 file, just like the service I show. It's a use file out HDF service to generate an HDF4 file through Hyrax DMRPP. So does that make sense to you?
So there is no physically, there is no an actual NetCDF4 file with there's data.
No, yeah,
All
this
on the fly.
is generated.
Sorry?
Hyrax. This file is just show you I generated through Hyrax. There's no NetCDF4 file.
Okay.
Yeah, only HDF4, no HDF4 file, only HDF4 hairs data. That's the local, that's the whole purpose, right? I want to show you here is just basically you can generate an HDF4 file through Hyrax. That's basically the most popular service Hyrax is used.
Okay, thanks, Kent. So you can stop sharing now, I think, or you stop sharing, right? So the next speaker is Luis Lopez, who is remotely as well. I'm hoping he's online.
I'm online. Can you hear me?
Excellent, excellent. Hi, Luis. So Luis is from NASA National Snow and Ice Data Center and from NASA OpenScapes, I think. And Luis is really was really helpful with this whole study of cloud optimized HDF5 files. He really helped a lot me and the HDF group to make things better and understand some issues, because we don't have the resources to try things on so many files and different things. And so I really want to thank him for that. And he's willing to work with HDF library audits here and there, as it improves its interface with cloud data access. So Luis, you can share and you can begin whenever you want.
Perfect. Can you see my screen?
Yep.
Okay, so let me go to slideshow. Can you see my full screen? I cannot see the chat, but I will assume that you can see.
No, everything is good. Sorry, I just moved away from and muted, so you're good.
Perfect. All right. So
Yes.
yeah, as Alexander was
You
saying,
can only move that annoying Zoom toolbar.
yeah, I don't know
yeah.
how can I hide it.
Just hide video panel. Oh, no, video.
Panel.
That's one. Where's the other one? There is another hide, I think, or something. No hiding? All right, then. Well, we'll leave it.
Oops. Yeah.
All right, go for it then.
So my name is Luis Lopez, and I work at the National Snow and Ice Data Center in Boulder, Colorado. And this work is not just me, it's a lot of people trying to work to improve access to data. And the use case, or the case that I'm about to talk today, was covered yesterday also for Andy Barrett on a different session. So a lot of the information that I'm going to tell you, probably you heard it before, but repetition until it sticks. So why this is important? ISAT is a satellite that was launched in 2018, October, I believe, and it contains the most precise laser altimeter in the world that it's in orbit. So the primary mission is to monitor the glaciers and how ice sheet around the world evolve, like to the precision of millimeters per year in change. Here you can see like a map of the data products that are generated by this satellite. And I'm just mapping a little bit of what it's one of the core products, where a lot of the other ones are derived. As usual, a lot of acronyms here, but ATL, it's kind of the acronym of the instrument, and O3, it's, I don't know, the consecutive number of but it's a level 2 product. It's geolocated photon. So the satellite shoots 6 laser beams. They get back, and the satellite can measure individual photons at the time. So that generates a lot of data. And this product, that it's the core product of the satellite, has about 900 different variables in their 6 different laser beam tracks. So it's a very complicated data set. On the right, you see, just as I said, just from one track, not even a complete list of the variables. So as you can see, accessing this information is not trivial. And why this is important? Well, because like thanks to these satellites like ISAT and the upcoming satellites and the satellites that are in orbit, we can answer questions that were not possible before. You can integrate the data from the different missions or a single mission. In this case, you're saying integrations only for ISAT mostly on two different things that affect our planet. One is the global sea ice concentration on the left, and on the right, you see the biomass from the boreal forest in the northern hemisphere. So in order to create this visualization, and the most important part, like a time series of how things are evolving, the scientists doing these studies had to integrate thousands of files, and that wasn't simple. Now, the good news is that this data is going to the cloud, and in the cloud, we'll be able to leverage, the scaling and all of that cool stuff. This is a kind of a historic chart of how much data has been served by NASA. And now the caveat of this is that most of this data is in HDF and HDF format, which is not legacy, but in a way it is. So that's the importance of the work that I think a lot of people are doing. And I'm presenting just the applications of all the amazing work that the previous speakers talk about. Going back into why this is slow, right? This is just like a funny way of putting it. But when the libraries and the formats were built, the cloud didn't exist. And although the storage had improved a lot, it's different from cloud storage. And you can see like in numbers, like going to memory takes a second, going to a disk read takes days, but going through over the network, in the best case scenario, will take years. So latency it's an issue when we're working with remote data. And now, because of the data in the cloud, we need to improve that. So orders of magnitude. So what that means, it means that it doesn't really matter where you're coming from. Like if you're working in a notebook, you're working in compiled code or a QGIS session, if we're accessing data over the network to open at HDF, we'll hit the issues that we know. And some of the issues are basically related to the format and how the library accesses it. So in this chart, little graphic on the right, you can see that for the most part, we are going to interface with the HDFC library because the format is very complex. So we can, and there have been people working on writing their own readers. I wouldn't advise that, but if you're technical, you could, but it's not simple. So once you read something from GDAL or something using another driver, basically we're hitting one of these two roads. We're hitting the native drivers on the left, or we're hitting the cloud-enabled drivers on the right. And that's one of the things that we want to improve is like, access. And for this mission, for ISAT, the first thing what we tried to do was to investigate what can we do to improve these things. And a year ago, or over a year ago, Alexander and his group, the HDF group, presented this actually in the last AGU, very kind of obscure poster about how to cloud optimize data in HDF5. So to me, that was kind of like when they announced the LK99, and that, oh, you can do superconductivity without, spending energy. So in one of the hack weeks organized by the mission, by the ISAT mission, me and others decided to give it a go and investigate, okay, let's try this stuff and see if it works. So the first results, were, very promising. And then we hit a lot of bumps, and I'll go into like a little bit technical here, but the gist of why HDF is not performant in the cloud is because, historically, it has been stored in, these little chunks of metadata. The metadata will probably account for most of this slowness. physically, you have to read the file. You get the magic of the file. Oh, yeah, this is an HDF file. And then the driver says, I can read it. And then the next read, it reads 8 bytes and then 16 bytes. And then it goes up in a progression reading metadata. But the progression ends at 4 kilobyte chunks. So each of this is the default coming from the library. If we write an HDF file into disk, it will have something similar to this in terms of layout. So these reads are very expensive, as we mentioned in the other slide about like the latency of these reads. By the time we, like in this case for ISAT, we had like, many variables, many nested data sets, and each of those data sets have to have some metadata describing attributes and dimensions and all of that. And with the global lock, that means that each of these requests is done serially. So one is blocking the next one, and until those end, we don't really have the data that we need. So it's just like, it takes forever to open that file. So when we do a file open with Python or better library like X-Ray or something like that, we will wait forever, depending on the data set. And in the case of ISAT, it was a lot. So a little bit about what we were testing is this page aggregation, which is the simplest way of cloud. It's not the only one, but it's the simplest. What it does is forces the library to read in pages. So when we create a file, we can repack it, but when we create the file, you have a dedicated page for metadata, and then the other pages are filled with data itself. What that allows us is that instead of like reading 4 kilobytes, you read the page size. And we had a lot of fun trying to figure out what is the correct page size for each data set or for our data set, because this is not like one size fits all. It depends on what's in the files and what is the access pattern. And in our case, we basically came to the conclusion that 8 megabytes it's a good compromise. Depending on the file size, of course, you have more or less metadata, because on top of everything, ISAT is not a ATL03, the product that we started to cloud optimize, is not a regular grid. So it's very variable depending on the readings of the satellite. You can have files with a lot of metadata or less metadata, and then the size that you're putting here will be across the products, across the different sizes. So instead of reading, the 4 kilobytes, we're reading like 1, 2, 3, 4 in fixed size pages. And then the library in the client side is decoding the information, but it's more efficient. Now, there is another way that I think down the road will be even more efficient if we come up with better chunking, of course, or that would be like the metadata blocks or user block. So all the metadata, it's in one block, and then the library will read the data chunks as they are. Right now, that is also not async or parallel because of the global API, global lock. So I got really excited with the previous talks about like having multi-threaded and I/O here, because if we have that and we implement something like this, and the library automatically reads, oh, so this file has like, I don't know, 8 megabytes of metadata, I'm gonna read it in one go, and then the rest, well, you decide, but I'll do it in parallel or async. That would be the best case scenario. And once that we run those optimizations, we notice, immediately the improvements, like from going to a minute, and this is in the cloud, to like 5 seconds. So we got excited and we thought like, wow, we did it. But turns out that once that we translated this into bigger files and bigger files, we run into issues like, oh, now the performance is not improving, it's decreasing. Why is that? Well, yeah, so we were like, oh, maybe this doesn't work because of the bigger file sizes contain something special. And so we did some investigations, and we noticed that we have a lot of moving pieces. So when we open, this is a library in Python called X-Ray that works with n-dimensional data. Not necessarily the best option to open this specific product, but the route to open this file is similar if we use a different library. So the library uses a file format backend that in turn uses an IO driver, could be the native HDF driver or the FSSpec, which is a library that virtualizes remote storage. So all of these libraries had like some particular settings that were not designed for, optimizations, and in particular the cache. So FSSpec or ROS have their own cache mechanisms, and of course that affected the way we would read the data. So this is something they probably saw yesterday, but once that we wanted to like access a file that was cloud optimized and one that wasn't, we had to use different parameters. So I think this is changing with new upcoming versions of the library, and the library will kind of adjust it. But at the moment, you have to basically do some calculations, and this is per file. So you kind of have to have an idea of like, okay, so this file was optimized with 8 megabyte pages. So that is, we need to use a multiple of that for this parameter, the page buffer size. So with each request, we can hold up to n chunks of data. And then the metadata plus the data. And that has to be aligned with the IO. And in the case of the FSSpec case, the library does something by default that is really an anti-pattern for binary data. It uses a cache called read ahead. And that is very slow for reasons that go beyond this talk. But well, once that we align the cache, we got the performance that we were looking for. And this, Andy showed this or better version of this. The gist of it is that you can access HDF using the native library once that you have the right parameters and all of that at the same speed that we can access the same file using Kerchunk, or in other words, as if we were dealing with SAR. And that is really great because you don't have to change the code. Well, you have to change some parameters, but the code remains the same. And one of the cool things about all of this investigation is that the mission itself, it's adopting the recommendations. And ISAT2 for the next version will be the first NASA mission to produce HDF, cloud optimized HDF. And a side benefit for data producers is, of course, the IO. On the right, you can see what happens with the normal, like 4 kilobyte reads. You get really small requests, a lot of IO, unnecessary IO. And on the left, you see the consolidated page aggregated version of it. As I said, it's not the only one, and it can vary a little bit, but it's order of magnitude. And what that means is that for cloud providers, some of them charge per get request or per operation. So if you have a lot of data sets hosted in, for example, S3, you can tell like this is going to be cheaper than accessing millions of times the same file. So it's really good in performance and also in costs. And once that we get to that point that you can have cloud optimized HDF, I think what can we do with that? Well, I'm envisioning a lot of cool things, like the same things that happen in the SAR world or the cloud optimized GeoTIFF could be applied to HDF. You can have a spatial index, and I was just talking to Alexander the other day about like that, having operations on chunks directly with this GIS index and getting the data for different access patterns, so time series, because you know where the chunks are. These things on the bottom are different ways of accessing the HDF, but if the HDF that they're accessing is cloud optimized, well, then that will trickle down into like better access patterns for you and derived tools and pipelines. So I think the importance of cloud optimized HDF has been a little bit understated, and it's a must, because that's where most of the scientific data that we use to understand our world is stored. And I feel like the HDF group and people working on it are really not big in comparison to like the investment on other stuff. Like all these studies take years and a lot of money and effort, and the underpinning of that, it's not as this is my editorial note, it's not as well funded as it should be. And with that, I thank you and If you have questions, please let me know.
Thanks, Luis. I only want to say that poster that he showed that I made for the last AGU, actually, he was very kind to me this time. He said it was ugly, actually, so I just want to, he thought my poster was really ugly. So, just to be accurate. So any questions for Luis? Yes, where is the,
You want to just repeat my question?
yeah, I'll repeat, okay, go ahead.
So the question is, as I understand it, to capture the power of file optimized HDF, you need to both tune the file structure, but also tune your sort of reading parameters, right, to match that underlying file structure. So you need to know what the file structure is and pass those arguments through when you're reading the files, right? So page buffer sizes and all those sorts of things. Is there a way to do that sort of heuristically or on the fly based on sort of just when you read the initial file metadata, to just automatically say, okay, these are the page buffer sizes we need and other kinds of things? Or is that outside the realm of possibility?
So the question, Luis, was that beyond just optimizing the file itself, where currently it's needed to actually pass the right parameters throughout the, as you say, the API chain to get the performance that is desired. Is that correct? And is there any way to do, and I can answer your other question. And the other question was, is there any way that that can be essentially outsourced on the fly or some other way hidden from the user and user applications?
Yeah, so I think you answered a little bit of that, but it can be done. It's not automatic right now. So the idea, I think, Alexander, correct me if I'm wrong, but the idea is that the heuristics, it's kind of built in the library. So the library will inspect the file, see what is the metadata size, and it will do the smart thing to read if you're accessing it using the ROS driver, for example. But it's not there right now. So it's kind of like Alexander says, this is an F1 car and you have to manually tune it. So at the moment, a user will be responsible for, well, not responsible, but you're in charge of saying I have this chunking in my file and this is what the IO library is doing. So I have to match that to the chunking and the metadata that it's in the file. I think that's very complicated. It's something that I don't think about when I'm opening a cloud optimized GeoTIFF, and I'm hopeful that that will be the case soon with the HDF library, either through the native driver or through a different library. But yeah.
So
It can be done, right? I mean, the only
Can
thing
you-
I would
can
worry
you-
about is that,
you have to come in, yeah. We have someone who wants to answer, but needs to
yeah,
come
I mean,
closer.
it can be done. The only thing that I would worry about is that how much space do we use for the page cache, right? I mean, I could turn it on, I can have kind of a default for it. I mean, we have defaults for trunk caching, right? So, I mean, we could do this. This is a thing that could be turned on. Oh yeah, and there's a new chunk cache and stuff that can potentially help with this, yeah.
Set up new parameters, library with metadata cache will know when to increase chunk cache, and it will be shared between data sets. So it will be much more memory efficient and access efficient.
For those who are following along at home, Elena said that the new chunk cache that will come in with the sparse data format stuff will have the ability to auto adjust and be smarter about doing these things.
But yes, that's the future, and a lot of these cloud optimized files really we're able to deliver now because that's readily available. So just to be clear, a lot of things can be done, but then we're talking about time, resources, and obviously when it actually reaches the masses, because there is an uptake, there is a delay once we release a new version of the library before it percolates into all the package managers and those people decide when to upgrade and everything else. So yes, there is some work, just to finish answering my second, so there is some work to make this thing invisible or less required, but slowly, or let's say, increasingly, I would say. All right, thanks, Luis. No more questions, more questions? How are we doing? All right, no more questions, so who's next? Oh, that's me, okay. Thanks, Luis. Let's go back to the browser. So okay, just about the right time. Where is me? Oh, that's me. So I will be talking. Oh, where's the full view? There has to be somewhere. All right. So I will be talking about. Sorry. Oh, sharing screen. Oh, only that. Let me see. Where is Zoom? Oh, it's here. Oh. Sharing. So a lot of that I'll be talking about is really the result of working with people like Luis and sort of getting their feedback and trying to answer questions or problems and then thinking how to address them and what to do. So I really again want to thank NASA OpenScapes members and NSIDC ICET2 mission and NICER mission. Some people there who really found time and interest to work and try to shed more understanding of this situation with cloud optimizing HDF5. I think people here are fairly technical, so just, required glossary of terms, but stop me anytime you think you need something clarified. So I'm not going to talk about this. You now know that these cloud optimized files are not a new file format or in any way some kind of a special convention. That's really just reorganizing how the bytes in the file are laid out, and that's all. And fundamentally, there are two things. One is this consolidation of internal file metadata, and the other one is increasing chunk sizes. Again, that was possible. Bigger chunk sizes were possible forever. However, due to some historical reasons and default chunk cache sizes of 1 megabyte, the chunk sizes tend to be on the smaller side, and then it wasn't the problem really when files were in the file system, but now when the cloud computing came, that really started to show up its ugly side. And so for consolidating metadata, there were things that need to be done. And again, all of these things are actually available, I think, from library 110.1 or 110.2. So it's not new thing, just basically, no one thought about it before. I talked about all these methods last ECIP summer meeting. So here's the QR code to the video on the YouTube video that taught. So I'm not going to go into these details anymore. We are more about the applying those things and essentially what happens. So on the dataset chunk sizes, as I say, I'm very careful nowadays with this cloud optimized stuff that I differentiate between chunk shape and chunk size. So chunk size means I'm talking about bytes. Chunk shape means I'm talking about the actual part of an array that one chunk takes. And the reason why is that important is because you could, for example, have a chunk size of respectable several megabytes, but the chunk shape is still such that when you want to do certain slicing of the array, you will take a lot of these chunks, in which case you again going to have a poor performance because just you're touching too many chunks. So those two things are kind of connected, but then again, they answer different things. With chunk sizes, we're talking really network transfer. Chunk shape is again coming back to the data access patterns. And chunk size, again, the numbers that here I'm going to talk about are really before any compression or anything. These are the chunk size that would be in the memory. And when we looked into these things, although this line that there's these granules with larger chunks are difficult or rare, well, yes, but I actually found some. Just it happened after these slides were done. So I did found some granules with respectable 28 megabytes chunks and 40 megabytes chunks. So God bless them. But at the time, but they're fairly rare overall. And the other problem is even if you have a file with those smaller chunks, the H5 replec tool, which comes with the library, can help a little, but if you really want to hit a granule with thousands of data arrays to rechunk, it's not going to really be usable. And so we kind of had problems generating even with granules that we want to work. And so consolidating metadata, as I said, and as Luis mentioned, we really just explored this paged file approach, although there are two others. The paged file is convenient because it kind of lets you not think about have I sized things enough, especially for internal metadata. Because if it happens that you have a particular granule because of the data that you need to store there, your internal metadata is going to go over whatever size you thought to reserve. These pages are going to save you because as soon as there is more, there is another page for that stuff. And so things are still consolidated across multiple pages, but still more consolidated than would be otherwise. So I think that's why we kind of set up the page file approach mostly. And what is the advantages and disadvantages? Well, the advantages, and right now, as far as I know, the HDF5 library is the only benefactor of this, is that the library can read from the file in pages. So if you have a page with internal metadata, it's one read, you get all your information, what's in the file. If you have some data, again, you may get all the chunks in one page. Again, it's one read, you got all the chunks for your array with one read. So things can really be beneficial in that way. Further to that, the library can cache these pages beyond the chunk cache that we were talking about. So you can have page cache, you have chunk cache. So you can really cache these things with more sophistication than without using, when not using paged files. And then all, again, contributes hopefully to less S3 requests, which we all love. However, the disadvantage is that page files introduce file increase, because each page eventually will have some extra unused space. And so to what degree, how much, that's another story, depends. But that's something that can be bigger or less. And with the ISA2 mission, we found some interesting cases of how their products are generated that really could yield a really huge increase in file. Luckily, we were able to mitigate those issues so far, so we'll see how that goes. But yeah, so when you think about these pages, really, it's like you think this page like a box, and then things come into this box, and those would be chunks. That's for the data page. If it's a metadata page, those are the various information, what's in the file and where, like group names, attributes, creation properties, everything else. And so once that page gets filled, here comes another page. And so the file sizes of these paged files are very simple. You know the page, you divide it and you get an integer number, because it's just an integer number of pages. So current advice, again, when I say current, that's like as of last week before I left for this meeting. And again, mostly working with ISET2, with Luis and ISER mission and that kind of thing. How big they should be, really, we're talking about files, so not thinking about working across the files and everything else. We are now starting to think about filters and what role they play. And when I say filters in the HDF5 lingo, filter could be compression, can be any other modifier of the bytes. So most times the filters are compression, but they don't necessarily have to be. However, I think that the compression methods that are applied to these chunks have to be now revisited again. I think that there are now more sophisticated, better compression methods that we have to think about it. For many reasons, again, historically, the zlib or deflate or gzip, different names, same thing, was used for NASA satellite data, primarily because of interoperability concern. Zlib compression was widely available, so no one wanted to have that headache of using some compression that no one else can use or something like that. But I think that we should now start thinking about more advanced methods that can significantly reduce the data volume. And one of the reasons why is because smaller compressed chunks will go more into a single file page, which means that then increasing your probability that you have one page read and you get all your chunks for your array. So something to think about. The chunk sizes, again, we were looking to have a maybe up to 4 chunks per page. But again, remember, this 2 megabytes is before compression, because we don't know what's the chunk size after compression. It can be variable depending how the data compresses. So there is always a little slack there. But again, the point being is thinking the person who needs to decompress, not everyone will use Dask cluster, so that can dish out decompression to 60 nodes or something. Those free credits for using in cloud Dask cluster will run out eventually, I think, or something. So we have to sort of think about, the real life and that kind of stuff. But anyway, something to think about. But we can have a symposium on chunk sizes and chunk shapes. It's that kind of issue. For the paged files, I personally, and I think Luis also played with 4, 8, and 16 megabyte pages. Also, as you're increasing the pages, the file sizes increase, so that's something to think about. 8 megabytes or 8 megabyte pages seems to be sort of like a sweet spot between the latency of the requests and how much data one gets. So I think that would be the current sort of good recommendation, I would like to say. Most likely you will be able to have all your internal metadata in a single page with 8 megabytes or 8 megabytes. And as I said, depending on the content, the actual amount of data that's going to go with particular granule, sometimes these pages may be less full. So you think, oh my God, I'm wasting my storage. Well, don't think it like that. Think like investment in the future, that then the access is still going to be better. And so sometimes that progress comes at a price. But hopefully, again, with ISET2, I think ATL03 granules, couple of thousands that they tested, I think eventually came down to 0.1% increase. So I think I think it's 0.1. I checked, I think, yes. So one thing again to remember, because now we're creating these pages when we're doing the file, if there are more than a single open close session when the file is created, the library has to be told that I want to reuse the unused space in the current file. Because if you don't do that, the library will never touch the already existing file. And so for even the smallest amount of data, there will be another page that's going to be allocated. And so that's the reason how we basically managed to reduce the ballooning of file sizes for ISET2. The way how they were creating files, apparently there was a 3-time cycle of creating some file, then again closing, then again adding some stuff to the file, and then finally again adding some stuff. And before, without this optimizing unused space, just new pages were being added. The H5 repack can actually act as a defragmenter. You just run it on input file and then you give an output file, nothing else. And the H5 repack will basically try to recover this unused space, which was also helpful. And I don't have enough time, but this is in the slides. I wanted to show you what happens with some chunks in a page file. And I did a bunch of these statistics for a JEDI level 2 granule, which I get from another NASA OpenScapes member, I think Aaron Fries. I hope I didn't mention, for LPDEC as well. So I chose this one because I liked that it had 4,184 chunk datasets. So that was, oh, this is nice, just in a single file. So there's a lot of statistics there. And I just did 8 megabyte file page here, and I didn't touch the chunks. And so I looked, where are the chunks, what are the chunk sizes? And here's an interesting finding, that you have 1,100 chunks whose chunk size is less than 10 bytes. So basically that could be a no-no. Like, I'm not a person that says red flag, but this definitely should be a red flag. And so when you look like, but then again, to the credit, there are 192 arrays that have more than 10 megabytes chunk sizes. So kudos for that. So you see, you get everything in a single file. And so I'm not going to go through all of this now because we don't have time, we're close to finishing, but you see how many chunks are actually in the file also per each array. Interesting things, for example, when you look at the chunk spread across file pages. So here, 85% of the all chunks datasets, all of their chunks are in this one page. Now, it's not the same page, obviously, but it's only one page. So 85% of the time, if you read something from the file, there will be only one read, one page request to get the data. However, there are some that are sort of across between 6 and 9 pages, for example. So more reads are going to happen. This one is interesting. This is looking at, that the chunks are spread across more file pages than it would be required for their total size. So I call this anomaly. Maybe it's too critical. But, basically you have, chunks, and here, for example, 8 of them have, are really spread across these pages, although by their size in the file, they should not be. Anyway, this is an interesting one, talking about cache sizes. So I'm looking here, what if I had cache size set of these different sizes, 1, 4, 8, or 16 megabytes? How many chunk data sets would have all their chunks in this cache? And so as you can see, basically, again, 85% of them are okay with up to, say, 95% is basically 16 megabyte or less. So, that's not bad. But however, because of these big ones, 192, you really have to have chunk cache, in their case, more than 16 megabytes. However, again, you don't know that until you look into the file, and the library currently cannot be set after you looked into the file. So that's maybe this kind of optimization that have to happen once you know what case are you dealing with. The library is kind of designed with a manner that you have more understanding of your files than it's now required. And anyway, I don't want to talk about I already went a couple of minutes over, but that Dana talked about this as well. I want just to mention that this ROS3 driver, the read-only S3 driver, it's build dependent. The HDF group doesn't build with it. The H5 Pi, if it's pip installed, doesn't come with this driver as well. The only place for this ESIP crowd is the Conda Forge. The Conda Forge HDF5 package has this ROS read-only S3 driver built. So that's the current recommendation. And that's it. Thank you for coming. And any questions? Sorry, yes, questions? Yes, yes.
It's actually not a question, but
You have to come here.
yeah.
Because you're close. For others, I'm not going to ask.
Yes, just a comment that I think everyone in the community should be aware. In HDF5, it has an option when you compress the chunk that if a compression function doesn't work on your chunk, if the out buffer is bigger than in buffer, HDF5 will not write, it will write uncompressed data, and there will be flag, library will know that no filters are applied. Unfortunately, most of the filters, I believe all of them that we now provide, do not check for this option, and you may end up with a chunk size bigger than your original chunk. It's valid for the data that is mostly random if you're part of your data set. So be careful when you're working with chunk sizes and making your assumptions. This is one note. And the second note is chunk cache is important when you're accessing the same chunk many times. So if you're just reading and ingesting, chunk cache size is irrelevant. So that's why read documentation.
Which is ample, but sometimes we need it better. So good luck with that. But yeah, I just want to say yes. So cache, like any cache, if you never come back for the data or something, cache is useless. So yes. Luis raised the hand. Then I'll ask you. Okay, Luis, you can go.
Yeah. So I have like 2 questions, but one is that a lot of the knowledge to come up with, good defaults in the HDF library when we're writing files It's very, specialized, and data producers are not necessarily well, I mean, we can read documentation, but I feel like there is kind of room for improvement in terms of like tools that will help them take decisions on like what you analyze, basically saying like, oh, these are the statistics of my file right now. So I have like these chunk sizes that are really small, these chunk sizes that are really big, and it will give kind of like some basic advice of like, oh, like or flag the red flags in a file. I feel like there is like opportunity for a tool. I think you and others have been like playing with that idea too, of like I don't know how can we call it, chunk doctor or something like that.
Yeah.
Yeah, because like
We
how
can
many
do
of you
Dr.
are
Chunk,
there?
because we have Chunk, now we have a Dr. Chunk.
Dr. Chunk.
Dr. Chunk, yes.
So that's I guess the kind of question. What do you think about that?
No, I agree. And actually, I was thinking now, since Dana talked about this HEPS, HDF5, proposal process, that this could be also a candidate to basically discuss these things, how to do it. Because in diverse environment where you don't know, a lot about what data exactly going to be sized up in a file, then, some decisions have to be made sort of at the time when the file is created or something like that. And yeah, I agree. I absolutely agree. Yes, application, yes. Danny, you can ask, I'll repeat.
Okay, yeah, the question is, so you mentioned that if you do the consolidation of the metadata and with the paging, there's a slight increase in the file size
Yes.
in some cases. Is there any other like trade-off or downside for when we're not talking about cloud access, if for local file system access, does this consolidation of metadata affect performance? Yes. Does it?
It's not noticeable because there's the latency, right? But yeah.
Okay, but there actually is some.
I can actually quantify it because I tried with Jedi files that I got from Aaron. I got 1B, 2A, and 2B granules, and I created two versions cloud optimized, and then I compared them with S3 and on a local drive. And when it's in the local drive, the difference from the original one and this cloud optimized from the local file system that I ran was within 1 point some percent in performance. And I'm talking about milliseconds here. So this is not like you're going to notice it. That's important to mention.
But on systems with highlight this, you will. So HP systems, you will, right?
Yeah, but who uses HPC? I mean, please. I mean, come on. It's like, geez. So anyway, that's the that's the story. All right. Thank you.